Section: Introduction. In this section, we introduce Gemma, a set of open models based on Google's Gemini models. We trained Gemma models on a large amount of text data, similar to how the Gemini models were trained. Just like Gemini, these models excel in understanding and reasoning in text, covering a wide range of topics. We are making both pre-trained and fine-tuned models available, along with open source code for using them. Gemma comes in two sizes: a 7 billion parameter model for efficient use on GPU and TPU, and a 2 billion parameter model for CPU and on-device applications. Each size is tailored to different computational needs and applications. We provide raw pre-trained models as well as models fine-tuned for specific tasks like dialogue, instruction following, helpfulness, and safety. We thoroughly assess the strengths and weaknesses of our models using various tests. By sharing both pre-trained and fine-tuned models, we aim to encourage further research into the impact of different training methods and promote the development of safer model building practices. Gemma outperforms other similar open models in areas such as question answering, common sense reasoning, mathematics, science, and coding. It builds upon recent advancements in sequence models, transformers, deep learning, and large-scale training techniques. Gemma also draws from Google's previous work on models like Word2Vec, BERT, and T5. We believe that releasing language model models, LLMs, responsibly is crucial for enhancing the safety of advanced models, ensuring fair access to this technology, evaluating current techniques rigorously, and fostering innovation. While we have conducted extensive testing on Gemma models, users should perform thorough safety checks specific to their use cases before deploying them. In this technical report, we provide a detailed overview of Gemma's model architecture, training setup, pre-training, and fine-tuning methods. We evaluate all checkpoints across various benchmarks and discuss our approach to safe deployment. We also explore the broader implications, limitations, advantages, and conclusions of Gemma. Model architecture. The Gemma model is based on the transformer decoder and trained on a context length of 8,192 tokens. We have incorporated several enhancements, including multi-query attention, rope embeddings, JGLU activations, and RMS norm, to improve performance at different scales. Training infrastructure. We train Gemma models using TPU v5e in pods of 256 chips arranged in a 16 by 16 configuration. The 7B model is trained across 16 pods with a total of 4,096 TPU v5e, while the 2B model is trained across 2 pods with 512 TPU v5e. We use model sharding and data replication techniques within a pod and optimize the training process using JAX, pathways, and the Megascale XLA compiler. Section Summary. In this section, we introduce Gemma, a family of open models based on Google's Gemini models. Gemma models, trained on up to 6T tokens of text, achieve strong generalist capabilities in text domains and state-of-the-art understanding and reasoning skills at scale. We release pre-trained and fine-tuned checkpoints, catering to different computational constraints and applications, advancing performance across various domains like question answering, common sense reasoning, mathematics, and coding. Section: Carbon Footprint. In this section, we estimated the carbon emissions from pre-training the Gemma models to be approximately 131 metric tons of CO2 equivalent. This calculation was based on the energy usage data from our TPU data centers, accounting for both the direct energy consumption and the additional energy required to operate the data center. We converted the total energy usage to carbon emissions by comparing our energy consumption with the carbon emission data provided by our data centers. It is important to note that Google data centers are carbon neutral, achieved through various energy-efficient practices and the use of renewable energy sources. When it comes to pre-training, Gemma 2B and 7B were trained on 2T and 6T tokens of English data from web documents, mathematics, and code. These models are not multimodal and were not specifically trained for multilingual tasks. We utilized a subset of the sentence piece tokenizer from Gemini to ensure compatibility. The vocabulary size for these models is 256K tokens. To ensure the quality and safety of the pre-training data, we filtered out potentially harmful or sensitive content using a combination of heuristics and model-based classifiers. We also conducted targeted analyses to prevent leakage of evaluation set data and minimize the risk of generating sensitive outputs. The final dataset was determined through a series of evaluations on the 2B and 7B models. For instruction tuning, we fine-tuned Gemma 2B and 7B using supervised fine-tuning on a mix of text-only, English-only synthetic, and human-generated prompt response pairs. We also employed reinforcement learning from human feedback, where human preferences were used to train a reward function and optimize the model's performance. In supervised fine-tuning, we selected data mixtures based on side-by-side evaluations using different prompts to assess capabilities such as instruction following, factuality, creativity, and safety. Synthetic data underwent multiple filtering stages to remove sensitive information and improve model performance on various metrics. Formatting played a crucial role in training instruction-tuned models, as it helped annotate examples with additional information for better conversation understanding. Special control tokens were used to indicate roles and turns in a conversation, enhancing the model's coherence and generation quality. Furthermore, we utilized reinforcement learning from human feedback to further enhance the model's performance. Human raters provided preferences, which were used to train a reward function and optimize the model's policy. Hyperparameters were fine-tuned to prevent reward hacking and ensure the model's effectiveness. Section Summary. In this section, we estimate the carbon emissions from pre-training Gemma models to be around 131 tCO2 eq, considering energy usage from TPU data centers and additional energy for data center maintenance. We convert energy usage to carbon emissions using per-cell carbon emission data from Google data centers, which are carbon neutral. Additionally, we detail the training data, filtering processes, instruction tuning, supervised fine-tuning, and reinforcement learning from human feedback for Gemma 2B and 7B models to enhance performance on downstream evaluations and human preferences. Section: Evaluation. In this section, we evaluated Gemma in various ways. We conducted human preference evaluations by comparing Gemma models to Mistral v0.27b instruct model on different types of tasks. For tasks related to creative writing, coding, and following instructions, Gemma 7b-IT had a 51.7% win rate, while Gemma 2b-IT had a 41.6% win rate. On safety protocol tasks, Gemma 7b-IT had a 58% win rate, and Gemma 2b-IT had a 56.5% win rate. We also assessed Gemma models' performance on automated benchmarks covering areas like physical reasoning, social reasoning, question answering, coding, mathematics, common sense reasoning, language modeling, and reading comprehension. Gemma models were compared to other open-source language models on various benchmarks, where Gemma 7b outperformed many models, including larger ones like Llama 213b, especially in mathematics and coding tasks. Furthermore, we investigated the memorization capabilities of Gemma models to understand if they memorize training data. We found that Gemma models show lower memorization rates compared to other models like PaLM and PaLM2 when evaluated on shared training data. We also checked for memorization of personal data and sensitive information in the model outputs using automated tools, finding no instances of memorized sensitive data but some occurrences of potentially personal data. Overall, our evaluations show that Gemma models perform well across various tasks and demonstrate strong capabilities in mathematics and coding. We also took measures to ensure the safety and reliability of Gemma models by filtering out personal data during training. Section Summary. In this section, we evaluate Gemma across various domains using both automated benchmarks and human evaluations. We compare Gemma models against Mistral v0.27b Instruct in human preference evaluations, where Gemma 7bit shows a 51.7% win rate in creative writing tasks and coding, and a 58% win rate in basic safety protocols. Additionally, we assess memorization in Gemma models, finding comparable rates to PaLM models and no instances of memorized sensitive data, despite some potential memorization of personal data. Section: Approximate memorization. In this section, we observed that around 50% more data is roughly memorized, and this trend is consistent across different subcategories in the dataset. We follow a structured approach to responsibly develop and deploy our models, drawing from academic literature, industry exercises, expert input, and efforts to uncover new model vulnerabilities. We believe that openness in AI science can bring significant benefits, but we also acknowledge the risks of potential misuse. By releasing Gemma into the AI development ecosystem, we aim to enable developers to create beneficial applications in various fields. We have provided different model sizes and made them available on multiple platforms to support a wide range of developer needs. While there are benefits to releasing Gemma, we are aware of the risks associated with malicious uses of large language models, LLMs, such as deepfake imagery and dissemination of harmful content. We have implemented measures to mitigate these risks, including filtering biases in data, safety assessments, red teaming, and rigorous ethics evaluations. We have also published a model card for transparency and released a toolkit to support responsible AI development. Despite our efforts to enhance the model and address potential risks, we acknowledge its limitations. We are committed to ongoing research and development to improve mitigation strategies and ensure responsible AI use. We believe that the release of Gemma will have a minimal impact on AI risk overall and that the benefits it offers to the AI community outweigh the associated risks. Section Summary. In this section, we observe that approximately 50% more data is memorized, consistently across different subcategories in the dataset. We follow a structured approach to responsibly develop and deploy our models, drawing from academic literature, industry exercises, and expert engagement to manage societal impacts. While we acknowledge the risks of malicious uses of language models, we have implemented various mitigation strategies, including bias filtering, safety assessments, and ethical evaluations, to safeguard against potential harms and promote responsible AI development. Section: Going forward. In this section, we aim to align our assessments and safety measures with the risks posed by our models. We believe that our Gemma models will bring positive outcomes to the community. However, we prioritize safety due to the permanent impact of this release. Since the negative effects of open models are not clearly defined yet, and there is no standard way to evaluate them, we will proceed with caution in developing open models. As technology progresses, we may need to consider more extensive testing, gradual releases, or different access methods to ensure responsible AI progress. We encourage the broader AI community to move past simple debates of open versus closed, and to not downplay or exaggerate potential risks. We advocate for a collaborative and nuanced approach to understanding the risks and benefits involved. At Google DeepMind, we are dedicated to creating thorough evaluations and welcome the community to join us in enhancing our comprehension of AI systems.